Hey guys, it's Joseph here again with Prep for Step, and in this particular video we will be discussing iron metabolism. This is a pre-lecture for all microcytic anemias, specifically iron deficiency and anemia of chronic disease. If you intend on studying those, this is a good lecture to go through, because if you thoroughly understand iron metabolism, it'll be much easier to understand iron deficiency anemia and anemia of chronic disease. Now, the iron metabolism basically means there should be a balance between the dietary intake that we have and our iron loss that we have, okay? Now, the dietary requirements for a male is only 1 to 2 milligrams a day. That's all we need technically, okay? And female, if a female is menstruating, about 2 to 3 milligrams per day. If a female is pregnant, about 6 to 7 milligrams per day. So it goes up a little bit during pregnancy. But our dietary intake for Western societies is actually pretty good. That means that in a typical Western diet, about 15 to 20 milligrams a day of iron consists in a Western diet. That means that there's more than enough in there for us to absorb. But here's the key. Only about 10 to 15% of that is actually absorbed, and it's really tightly regulated, okay? Now, the dietary iron, it comes in two forms. One comes in heme, and the other is the Fe2+, or the Fe3+, or the ferric form, okay? Now, the way we lose iron, and this is something to remember if you've ever studied or heard about hemosiderosis or hemochromatosis, and that is when you get iron overload. Iron loss is only via the intestinal epithelial shedding. Means that when you go to the bathroom every day and you shed intestinal epithelium when you defecate, that's how you actually lose iron. It's the iron stores inside the intestinal epithelium that actually causes you to lose iron. There's no other way to lose iron. You could bleed, but that wouldn't be something that you would actually want to do on a daily basis. So the only way to get rid of iron is through epithelial shedding. And this is why the absorption must be tightly regulated, because if you absorb too much, or for some reason you have too much iron, iron is highly toxic and can be deposited into the tissues. Okay, so why is it with all the blood that we have, a few liters of blood, half of that being, red blood cells and stuff, how is it that with all that hemoglobin, we only need about 1 to 2 milligrams of iron per day, or 2 to 3 milligrams of iron per day? Where does all the rest come from that we build hemoglobin? And the idea is that we actually recycle iron in our body. RBCs live about 120 days. After 120 days, they pass through the spleen. And in the spleen, there are some guys called macrophages, okay? These macrophages actually eat up the old RBCs, and they sequester and hold the iron that they took out of the dead RBCs. They hold that iron inside themselves, and they release it very meticulously and very in a systematic manner, okay? And that's, they release it in response to some hormones, and then we can actually build new red blood cells. Now, the total iron in our body can be divided into two groups. One is functional, means it's working at any given time, and the stored. The stored iron is stored, whether it's stored in the liver or the spleen and bone macrophages, that means it's just stored, okay? But the functional, is actually working. 80% of our functional iron is actually in our hemoglobin. So at any given minute, 80% of our functional iron is actually in our hemoglobin and our red blood cells circulating, helping our tissues with oxygenation. The other 20% of our functional iron is usually in myoglobin, enzymes that actually require iron, such as catalase, or in cytochrome, such as cytochrome C that we see in the electron transport chain that helps us, build ATP and give us energy, right? The stored iron is usually stored in two different ways. Okay, it's stored in three places: liver, the spleen, and bone macrophages. Not the liver macrophages, but actually the liver parenchyma, the liver cells itself. But the spleen and bone, it's stored in the spleen and bone macrophages. Now, it's stored in two different ways. It could be stored as hemosiderin, or it could be stored as ferritin. All right. Now, normally the stores of the liver comes from plasma iron. All right, but the spleen and bone macrophages, their stores usually come from breaking down old RBCs, which makes, complete sense. Now, how is iron transported in the blood? Iron is very toxic to tissues and can be deposited into, the heart or kidney, and then the macrophages will go try to eat up and damage that particular tissue. Could damage our heart and damage our kidney, which is called, hemochromatosis. So we don't want free iron levels running around in our body. All right, so what we do is we have something called plasma ferritin, which is a good indicator of our iron stores. So if I tell you that the person's plasma ferritin is high, that means that they most likely have high levels of stored ferritin as well. All right, so a person that is iron deficient means they have low plasma ferritin levels, or that means that they have low storage iron as well. And this is going to be completely useful to you when you're trying to differentiate between a iron deficiency anemia versus anemia of chronic disease, and that'll be in our next lecture. Now, transferrin is a protein. Transferrin is a protein that's made by the liver, and imagine it as a bus. This is how I like to look at it, just as a bus. Okay, it has, let's say, 30 seats in it, and at any normal iron levels, it's only 1/3 full. So it's only 33% saturated at normal iron levels. So 2/3 of the bus is actually empty. And that empty part correlates with our binding capacity. The more binding capacity that we have, that means that our saturation level is lower and lower. Okay, so TIBC, or total iron binding capacity, is the capacity of this transferrin to actually accept more iron. That means that the more empty seats they have, or the less saturated they are, the more capacity they actually have to bind new iron or bind other iron. Okay, so now we're going to discuss the iron absorption and its regulation, okay? And the way we're going to do that is, this is our gut right here. This is the lumen of our gut. This is an epithelial cell, and this is going to be our blood. The idea is to get the iron across the epithelial cell and then dump it into the blood. And that's how we actually absorb that 1 to 2 milligrams or 3 milligrams of iron per day. Now, the iron in our diet can be as heme, or it can be in the form of a ferric state, or the Fe3+ state, okay? The heme, there's a heme transporter on the epithelial cell, so the heme can easily just come across and get inside the epithelial cell. No problem whatsoever. The problem comes when we're talking about the Fe3+, or the ferric state of iron. This cannot get across the actual epithelial membrane, so it first has to be converted to the ferrous state via something called cytochrome B. So cytochrome B converts it to the ferrous state, and then the ferrous, through something called a DMT1 transporter, or divalent metal transporter 1. This can actually take the ferric in, and now we have the ferric inside the epithelial cell. Now, two things can happen. These guys could actually stay inside the epithelial cell and contribute to the intraepithelial mucosal iron. And this iron is basically what we shed every day when we go, when we defecate, okay? So when we defecate, we're getting rid of 80% of it is basically getting rid of all of these intestinal epithelial cells, and they all have storage of mucosal iron, so that's how we get rid of our 1 to 2 milligrams of iron per day. And that's why we need more every single day. So the heme, or the Fe2+ could also turn into Fe2+. So the heme, if we're trying to get this heme, we actually have to convert it to Fe2+. And this is already Fe2+, so we won't have a problem. This guy, this Fe2+, now needs to leave the intestinal cell and get actually outside of the intestinal cell, and that is done by ferroportin 1, or ferroportin, okay? So now Fe2+, or the ferrous, the iron in the ferrous state, has left, but guess what? Again, the iron as ferrous cannot be transported in the blood on transferrin. It actually has to be converted, and it has to get converted back to the ferric form. And that is done by hephaestin, or hephaestin, okay? That's another molecule right here. And that converts Fe2+ to Fe3+. And now the Fe3+ can actually get and sit on top of the transferrin. Now, what happens on side of the transferrin, based on our body needs, the transferrin can actually, and these are all Fe3+, and the reason I only draw 2 here out of 6, that's to tell you the 30% or the 33% saturation level. So at any given time, this transferrin has, 60% of its spots are actually available. Okay, and that's the binding capacity. The binding capacity is basically the available seats on transferrin. Now, if we need to produce red blood cells, This transferrin can go to the bone marrow of flat bones, such as the skull or the pelvic bone, and then we can produce red blood cells in response to a hormone that comes from the kidney called erythropoietin. Or this plasma level, or this plasma Fe can actually go to the liver. In response to this, in response to receiving Fe or receiving iron, the liver will produce something called hepcidin. This is really, really important to understand. This hepcidin acts as a plug to ferroportin, okay? So it is the liver that's going to put a cap on this ferroportin, thereby regulating the absorption of iron throughout the day. If the liver doesn't receive iron, that means we need more iron we need to absorb more iron. So liver will not produce hepcidin. But if the liver receives a lot of iron, it's going to produce a lot of hepcidin, and that hepcidin will actually block the ferroportin. Therefore, we won't absorb any more iron. The rest of the iron that we talked about comes from the spleen macrophages and the bone macrophages, which they break down red blood cells and they keep the iron inside themselves, and then they release them systematically. This is the dietary part. The other part I just went over, and I didn't draw any shapes for it. So this is very good and very important to understand if you're trying to study microcytic anemias, anemia of chronic disease, or iron deficiency anemia. Okay, hope you guys enjoyed it. We'll talk to you next time.